Have you ever wondered why the colorful blobs of lava in a lava lamp continually go up and down? It has to do with the process of heat transfer. We have already learned that heat flows from a region of higher temperature to one of lower temperature. How is the heat transferred? One way is by a process known as heat conduction. Remember that when an object is heated to a higher temperature, its molecules move around more vigorously. Heat conduction can be visualized as the transfer of heat energy from the hot end of an object to the cold end of an object via molecular collisions along the object. In an earlier section, we learned that fluid flow in a pipe was proportional to the pressure gradient along the pipe. Visualizing heat transfer in an analogous manner, what is the heat flow per time interval proportional to?
Correct.
It's the temperature gradient. There's still another important parameter that affects the rate of heat flow. Can you think of what it is?
Correct.
It's the cross-sectional area of the object where the flow is occurring. Adding in a proportionality constant, K, known as the thermal conductivity, we have our equation for determining heat transfer in an object. The SI units used for heat transfer are joules per second. The thermal conductivity varies greatly for different materials. Which materials transfer heat the best?
Correct.
It's materials with high thermal conductivities, like metals. We call such materials good heat conductors. Materials with low thermal conductivities are called insulators. Metals are good conductors because they have a lot of free electrons bouncing around that aid in transferring the heat energy. In the United States, insulating materials are given an R value, which is defined as the thickness of the material divided by its thermal conductivity. R values in the United States are measured in British units. It's important to remember that a larger R value means a better insulator. Now let's look at an example of heat transfer. We have a house built with a 1 centimeter thick concrete wall, an outside temperature of 15 degrees Celsius, and an inside temperature of 20 degrees Celsius. How thick would an aluminum wall have to be in order to have the same rate of heat flow through the walls? First, we write down the heat flow equations for the concrete and aluminum walls. What should we do next?
Correct.
We set the two equations equal to each other because we want identical heat flows. Next, we see that the area and temperature terms are the same on both sides. So they cancel out, and we are left with just the thickness and conductivity terms for concrete and aluminum. Rearrange the equation in order to solve for the aluminum thickness term. Finally, enter the thermal conductivity values and the thickness of the concrete wall to determine the thickness of the aluminum wall. We find that a 2.4 meter thick aluminum wall has the same rate of heat flow as a 1 centimeter thick concrete wall. Liquids and gases are generally poor conductors of heat relative to solids. Why do you think this is so?
Correct.
The molecules in liquids and gases are usually farther apart than in solids, and therefore can't interact as well to transfer the heat energy. Looking at our lava lamp again, we can see that conduction of heat through the base warms the lava. However, that doesn't explain why the blobs of lava move up and down. What causes that?
Correct.
It's convection. Convection involves the transfer of heat by the mass movement of molecules from one place to another. In the lava lamp, the lava near the heater in the bottom becomes heated and rises upward as hot blobs. The blobs cool and fall back down, completing the cycle. We see examples of convection all around us. A pot of water used for cooking heats up more effectively due to convection currents in the water. A furnace heats a home more effectively by forcing a convective cycle through the use of a fan and hot and cold air registers. It is important to note that conduction and convection both require interactions with matter in order to transfer heat energy from a hot to a cold region. Yet, the vanes of a Crookes radiometer spin when heated by a light source, which is not in physical contact with it. How do you think the light source transfers heat energy to the radiometer vanes?
Correct.
By radiation. But before we can explain how the Crookes radiometer works, we need to learn a bit more about radiant energy transfer. Radiant energy transfer involves the emission and absorption of electromagnetic radiation, and therefore does not require a medium for heat transfer to occur. What parameter do you think the rate at which an object radiates energy depends upon?
Correct.
The rate depends on its temperature. There's another parameter upon which the rate depends. What is it?
Try again. Correct.
The rate also depends upon the object's surface area. The rate of radiation is described by the Stefan-Boltzmann equation, where E is the emissivity, sigma is the Stefan-Boltzmann constant, A is the surface area of the object, and T is the temperature of the object. The emissivity can range from 0 to 1 and is characteristic of the material makeup of the object. What type of object do you think has an emissivity close to 1?
Try again. Correct.
A dark object has an emissivity close to 1, whereas a shiny object has an emissivity close to 0. We can see that even a small increase in the temperature of a body will have a large effect on the rate of emission. Approximately how much greater is the rate of radiant heat output for an object at 1000 degrees Celsius than the same object at 250 degrees Celsius?
Correct.
It's about 256 times greater. If an object is good at emitting radiation, how do you think it is at absorbing radiation?
Correct.
A good emitter is also a good absorber. A perfect absorber with an emissivity equal to 1 is known as a black body. Now we can explain why the vanes in the Crookes radiometer spin when exposed to a light source. A closer look at the radiometer shows that each vane is black on one side and shiny on the other. As we have learned, the black sides absorb more radiant energy and become hotter than the shiny sides. The inside of the radiometer bulb is not a perfect vacuum, so it contains some gas molecules. A flow of gas molecules around the vane edges from the cold side to the hot side drives the spinning vanes. The absorption and emission of radiant energy by an object can both be described by the Stefan-Boltzmann equation. If an object and its surroundings are not in thermal equilibrium, then there will be a net flow of radiant energy which depends upon the temperature, T1, of the object and the temperature, T2, of the surroundings. Now, let's look at an example. Suppose we take some cookies out of the oven at a temperature of 200 degrees Celsius and place them on a wooden tray to cool at a room temperature of 20 degrees Celsius. Assume they cool only by radiation from their upper surface. What is the initial rate of heat loss from one cookie? The area of a typical cookie is 50 centimeters squared. How many meters squared is that?
Correct.
It's 0.005 meters squared. We'll assume the typical cookie emissivity is rather low, say about 0.1. So what is the initial rate of heat loss per cookie? It's about negative 0.045 watts. For the next batch, we double the size of each cookie's diameter. How does this affect the initial rate of heat loss per cookie?
Try again. Correct.
The heat loss is 4 times greater. It is important to note that heat transfer in the real world often occurs via more than one process simultaneously. With our lava lamp, heat is conducted through the base to the lava. The lava transfers heat to the top via convection, and the lava cools by radiating heat to the room. Automatic toasters were around long before the advent of microprocessors. Have you ever wondered how a toaster knows when to pop up your Pop-Tarts? It's really very simple. A look inside reveals that two metal strips bonded together bend when heated, moving a catch bar, which eventually releases a spring-loaded catch that pops up the Pop-Tarts. The reason why the metallic strip bends when heated has to do with the topic of thermal expansion of materials. Most substances expand when heated. The expansion of an object in one direction is known as linear expansion. We already know that the change in length of an object depends upon its change in temperature. What else do you think linear expansion depends upon?
Try again. Correct.
It also depends upon the original length of the object. Adding a coefficient of linear expansion, A, which is characteristic of the material, gives us our equation for linear expansion. Now, suppose we have two thin rods of the same material, where rod 1 is 10 centimeters long and rod 2 is 5 centimeters long. What is the ratio of the final length of rod 1 to that for rod 2 after they both undergo a 10 degrees Celsius temperature increase? The change of length is just L minus L sub 0. After substituting this term into our linear expansion equation and rearranging, we can derive an equation for the final length of a rod. Rod 1 expands twice as much as rod 2. Suppose we have a thin strip of steel bonded to the bottom of a thin strip of aluminum. If we heat this bimetallic strip, what will happen to it?
Correct.
Correct. The bimetallic strip will bend downward because the aluminum expands in length more than the steel. This is how our toaster release mechanism worked. The two metals in the bimetallic strip expand differently when heated, causing the strip to bend and eventually cause the release of the spring-loaded catch. Now, suppose we have an iron ring that isn't quite big enough for the iron ball to go through it. What do you think happens to the diameter of the ring after we heat it to a higher temperature?
Correct.
The iron ring expands upon being heated to a higher temperature. Its diameter subsequently increases, allowing the iron ball to pass through it. Suppose that instead of a ring, we have a square sheet of aluminum with a circular hole in the center. What do you think happens to the diameter of the circular hole after we heat the aluminum sheet to a higher temperature?
Correct.
The diameter of the hole increases. Looking at the problem a different way, suppose we had a solid sheet of aluminum with a circle drawn in the center. It's now easier to imagine that the diameter of the circle increases as the entire sheet expands upon heating. Of course, things don't just expand in one direction. They expand in all three dimensions. In fact, linear expansion has no meaning with regard to liquids and gases, because they have no fixed shape. The equation for volume expansion is very similar to that for linear expansion. The beta term is known as the coefficient of volume expansion. How do you think the coefficients of volume expansion for liquids and gases compare to those for solids?
Correct.
The coefficients of volume expansion for liquids and gases are relatively much larger than those for solids. It is important to note that not all substances expand when heated. Water, for example, expands when cooled from 4 degrees Celsius to 0 degrees Celsius, and it expands even more when it freezes to ice. The resulting lower density is why ice floats on water.